it with cranberry juice. Not all the way. Up to here. Pack of pads. Put it on top. Table is beautifully set. Turkey, everything is there. And you suggest to your parents that you turn this over. Your mother will scream bloody murder. Because she would think that the cranberry juice will fall out. In fact, it may actually fall out. I can't guarantee you that it won't. But it may not. In which case, you have now all the tools to explain that. Today, I would like to test one of the students who no doubt is more powerful than I am. And I have here a funnel with a ping pong ball here, very lightweight. And we're going to have a contest to see who can blow it the highest. I have two funnels, very hygienic. I will try it with this one. They're clean, we just got them from the chemistry department. And so I would like to see volunteer, woman, or man, doesn't matter. You want to try it? See whether you can reach the ceiling? You don't want to try it? Come on. You want to try it? You're shy, you don't want to. Can I persuade you? I can. Okay, come on. Come right here. You think you can make it to the ceiling? It's only a very light ping pong ball. So you go like this, blow as hard as you can. Try it, don't be nervous. Straight up. Blow as hard as you can. Get it out. Amazing. Do it again. Come on, there must have been something wrong. You're not sick today, are you? Blow. Harder. No, there's nothing. There's no trick in here. My goodness, I mean, this is a ping pong ball. I'm not a magician. Come on. Blow it up. Hey, it doesn't work. It's amazing. Why don't you sit down? Why doesn't it work? Why doesn't it work? The harder you blow, the least it will work. Air is flowing here. And right here, where there's very little room, the air will have very high speed, way higher than it has where it has lots of room. And so, at the highest speed, you get the lowest pressure. And so the ping pong ball is sucked in while you're blowing it. And to give you the conclusive proof of that, I will do it this way. I will put the ping pong ball like so. And I'm going to blow like this. And if I blow hard enough, the ping pong ball will stay in there. Because I generate a lower pressure right here where the passage is the smallest. But I have to blow quite hard. See that? Isn't it amazing? That's the reason why she couldn't get it up. That's what Bernoulli does for you. Not so intuitive, is it? And I'm going to transfer this liquid from here to here. So first I have to fill it with cranberry juice. And there it goes. And as long as this level is below that level, it keeps running. Not so intuitive. I remember I was at a summer camp when I was maybe 6 or 7 years old. I couldn't believe it when I saw this for the first time. We had these outdoor sinks where we washed ourselves and brushed our teeth. And the sink was clogged. It was full with water. And one of the camp leaders took a hose, sucked up, and it emptied itself. And I really thought, you have to take spoonfuls of water or maybe buckets and scoop it out. This is the way you do it. Very non-intuitive. The non-intuitive part is that it runs up against gravity. Now it only happens during the acceleration. So it's only during the very short portion that I accelerate, that you see the apple go back. And then of course it starts to swing, forget that part. So watch closely. Only the moment that I accelerate, the apple will come this way. Goes into the direction, the extra component of perceived gravity. Ready? Boy, it almost hit this glass here. Everyone could see that, right? Okay. Now we're going to do it with the balloon. I'm going to take this one off. And now let's take one of our beautiful balloons. We're going to put a balloon in here. It has to be a closed compartment so that the air can build up the pressure difference. Okay. Only as long as I accelerate will the balloon go in forward direction. So I accelerate in this direction, and what you're going to see is really very naughty. The balloon went this way. No way of knowing. All you know is that the weight of the displaced fluid that you see here is the same as the weight of the object. That's all you know. If I took this object and I tilt it a little, which is somewhere here, it is stable. I can wobble it back and forth, and it is stable. If I would turn it over, then it's not stable. The displaced further. This torque will drive it away from the vertical. And that's very important, therefore, with ships, that you always build the ship such that the center of mass of the ship is as low as you can get it. That gives you the most stable configuration. If you bring the center of mass of ships very high, in the 17th century, they had these very massive cannons, which were very high on the deck, then the ship can capsize. And it has happened many times, because the center of mass was just too high. So here, the center of mass is somewhere here. Very heavy, this part. And so now, if I lower it in the water, notice it goes into the water to the same depth, because the buoyant force is of course the same, so the amount of displaced water is the same in both cases, but now the center of mass is high, and this is very unstable. When I let it go, it flips over. Coming out. Take a ping pong ball, stays there. Is that due to Mr. Bernoulli? No. No, that's more complicated physics, because it has to do with turbulence, it has to do with vortices, which is very difficult. And it will still stay there.